Okay, so this is the review session for a review video for EGME 441, midterm 2 for fall 2022. Okay, and so for midterm 2, this is everything about human dynamics, and so this is all about human movement. And so we had four, I would say, big topics, or at least the topics that we could cover before the midterm. And so what I thought I'd do is I thought I'd do kind of a quick review of kind of the most important points of each topic. And then, hopefully that'll take about an hour, and then that'll be the review video. Okay. Okay. So let's start with gait biomechanics. And so that was the first thing that we covered in human motion. And so gait was all about walking, and so locomotion. So walking, running, and so we talked a lot about that. And the reason what we started with this, normally when you kind of first start a new unit, you start with kind of the basics, and then you kind of work your way up from there. I think with human motion in particular, there's a lot of, I would say each kind of subcategory that you kind of see here is very detailed in terms of what's covered. I think it's easy to kind of lose sight of kind of what we're trying to look for and kind of the overall picture. And so that's the reason why I started with gait biomechanics, because I think it kind of incorporates a little bit of everything that we're going to go over eventually in mechanics or dynamics, I should say. Okay. All right. So gait biomechanics. This is all about. It's all about locomotion. So how do humans, well, specifically for us humans, but you can also apply this to other animals as well. How do animals kind of walk from one place to another? Okay. All right. And so what we started with was what I called the walking gait cycle. And so the typical stage of the typical events that occur as you walk from one point to another point. Okay, so I'm not going to draw the full diagram here. I'm not going to describe every single term here, but I think the kind of the most important points are relevant. Okay, and so the kind of what's characteristic of walking, or what kind of clearly defines walking compared to other forms of locomotion, or I guess running, is that you have what's called a double stance phase, and so you have or double support phase, and so that's a phase or part of the walking gait cycle where both your feet are planted on the ground. Okay. And once again, we call this a double support phase. Okay. And so unlike running, we have a flight phase. At all points in walking, you always have at least one foot on the ground, sometimes two. And so the part when you have both feet on the ground, that's called double support. Okay. And so from there, we can describe kind of the gait cycle for each individual foot. And so for each foot, we have a stance phase. Okay. And so this is the part of the gait cycle where the foot actually is on the ground. Okay. And then we have a swing phase. And this is the part of the gait cycle when the foot is off the ground. So it's either, you just picked it up and you're kind of moving it forward to the next step. Okay. So as an example, let's say that we have a person walking here. So let's just say that they just put their foot down. Okay. Okay. And so if we focus on the foot here that's not dotted, this would be part of the stance phase because the foot is on the ground. But eventually, this person is going to put their foot up. Okay. And so under that circumstance, when the foot is or the leg is kind of bent, the foot is off the ground, we call that the swing phase. Okay. All right. And so besides that, we have other terms that can describe the different parts of walking. So I'm not going to go through all of them because I think they're fairly basic. But there are things like the step length, the stride length, the step frequency, stride frequency, and the walking speed. Okay. And so I think the homework problems from homework 4 kind of covered this pretty well. And so, there's not much more to say about that. And so the next part after we went over the walking cycle is this concept of the ground reaction forces, and this is a concept that we didn't really realize until or we didn't really revisit again until we did inverse dynamics, which is kind of what we just finished up last week. Okay. Okay, so the idea with the ground reaction forces is that, as a person walks and as you kind of interact with the world itself, there's going to be external forces that act on your body, and it's only those external forces that can actually propel you forward or can actually, move you in some different way. Okay. Okay. And so, measuring these ground reaction forces and kind of seeing their values is something that's really important for human dynamics. Okay. And kind of as we saw, this is kind of looking ahead to inverse dynamics. We need these external forces, or we need these kind of reaction forces to determine or to compute what are the kind of resulting forces that are occurring inside the body. Okay. Hello to my cat. Okay. So I'm not going to say too much more about the ground reaction forces here. And we definitely go into this a lot more when we get into inverse dynamics, but we kind of reviewed it in the gate biomechanics, and so we'll go over it then. Okay. All right. One thing that was unique to walking gait biomechanics that we didn't really expand upon later on was this idea of a model or mathematical model or different ways that we can look and analyze the biomechanics of walking. Okay. Okay. And so the idea with biomechanical models is that in reality, the human body is much too complex for us to analyze in its kind of straight up fashion. And so in order to make the analysis simpler for us, we often have to make simplified models so they can highlight different aspects of the of our subject. Okay. Okay. And in particular, for walking and running, we talked about kind of two, I would say, very elegant models that can be used to model a lot of their interesting behaviors. Okay. Right. And so for walking, the model that we used for this was, remember the inverted pendulum. Okay. And so it looks something like this. Okay. And the model that we used for running was that we used an elastic spring. Okay. Almost like a pogo stick. Okay. All right, so these are, two fairly simple models because, pendulums are something that you've probably covered before in a previous class, and springs are definitely something that, we've talked about earlier in this class, but, you've certainly talked about them in previous classes as well. All right. And, what was most interesting about these, and I think one of the more interesting points about walking and running is how different their energy profiles look like. And so if you measured things like the potential energy and the kinetic energy as a function of time, what you'll see is that, both walking and running exhibit very different behaviors. Okay. Okay. And so let's talk about walking first. And so walking, one way that you can characterize walking is that it seems like a very kind of passive activity. Okay. And the reason it's called that is because the muscles, besides just supporting your own weight, the muscles actually don't do all that much during walking, and you can kind of see this exactly from the energy breakdown. Okay? Okay? The reason it's said that muscles don't do that much during walking is because you have this exchange between gravitational potential energy and kinetic energy, such that the entire kind of sum of the energies kind of always stays roughly constant. Okay. And so if we were to draw the energy history, so on the x-axis here, I have time. On the y-axis here, I'll have energy. Okay. During walking, it kind of looks something like this. And so, let me go ahead and draw in red right here. Okay. And so in red right here, we'll call this the potential energy. Okay. In blue, this is the kinetic energy. Okay. And so as you step, your center of mass kind of goes up and down, kind of, as you step down and go up and stuff like that. Okay. And so walking, through evolution and through kind of the science of design of the human body, we've learned to kind of walk in a very, very efficient way where, we're kind of just kind of pushing our weight down and then kind of using that gravitational potential energy to kind of push us forward. Okay. And so you kind of have this kind of continuous exchange between these two energies, just like a pendulum would, right? And so if you think about how a pendulum acts, right, a pendulum also kind of alternates between kinetic energy and potential energy. And so when the pendulum is at its highest and the motion is zero, so there's no velocity, that's when potential energy is at its highest, and then it's going to come down. Okay, when it's at its lowest point, the potential energy is at the lowest point, but the kinetic energy is the highest, and it goes back up like that. Okay. And if you've seen a pendulum act, a pendulum is largely passive, and so you don't really need to supply it with that much energy, except for getting started. Okay, and so walking is very similar. And so when we talked about biomechanical models, when we talked about the inverted pendulum, or I think we called it also the ballistic model for walking. The reason we did that is because of the energetics of the problem. Okay. Okay. All right. And so in contrast, the running model is more like a spring. Okay? Right? And so when running, um, what happens is that when you step down in running and when you kind of push off, right? Remember, the idea of running is to kind of accelerate or to go as fast as possible. And so the way that we do that is we once when we're in the stance phase, kind of when we're kind of down low, the muscles kind of build up a lot of energy, and then as we exit the stance phase, the muscles kind of explode, and so they kind of contract and they kind of release a lot of energy, and that allows you to kind of move forward and maximize your kinetic energy. Okay. And so if you were to draw out the potential energy and the kinetic energy, specifically the gravitational potential energy and kinetic energy, you'll actually see that these two are actually aligned. Okay, very much the same way as if you were kind of moving forward on a pogo stick. All right, so I'll use the same colors here. Okay. And so they're pretty much in phase. What you don't see here is actually We have another form of potential energy, but that potential energy is in terms of kind of energy storage within the muscles. Okay, so that's kind of be kind of like that. Okay, right. And so I think this was kind of the highlight of the gait biomechanics section. And so that, we could take kind of the basics mechanics of walking and running. We can see what they're similar to. We can make a model for these, and then we can use that model to analyze its behavior. Okay. And so for walking, we use an inverted pendulum because walking involves the continuous exchange between kinetic energy and gravitational potential energy. And for running, we have a spring model, which just shows how the muscles kind of store energy during walking. Okay. Okay. All right. And so that's it for gait biomechanics. So next, let's go into muscle dynamics. Okay. Right. And so with muscle dynamics, this was a section that we went over before. And so we covered muscle biomechanics kind of very early on in the class. But my idea with this section here was to kind of expand on it, with relationships that are relevant to motion. Okay. And so for this review, I'm only going to kind of focus on the expanded content. Because all the other stuff about actin, myosin, we covered that before. And so, I want to focus just on the new stuff. Okay. And a lot of this new stuff that we covered in muscle dynamics had to do with muscle performance. And so first of all, what are some of the properties of muscles that kind of contribute to its performance? And also, what are the conditions of the muscle fibers that lead to increased performance? Okay. All right. And so the first aspect of performance has to do with a force length relationship. Okay. So let me pause this for a second. Sorry about that. Okay, and so there are optimal lengths that the muscles for them to have optimal force generation. Okay, because what we saw was that this goes for every muscle in the body. There's kind of a sweet zone, and so if the muscle is too short, and so if it's kind of contracted too much, or if it's too long, or in other words, if it's stretched too much, it kind of limits how much force the muscle can generate. So there's kind of a sweet spot kind of in the middle where the muscle can produce optimal amounts of force. Okay. Okay. And the reason for this kind of very simply is that, the amount of force the muscle can generate depends on how many protein filaments, how much they can overlap, and how much they can contribute to a power stroke. Okay. And so there's kind of an optimal length kind of in the middle where you have optimal lining up between the protein filaments. Okay. And so if you were to draw the graph, and so on the x-axis here, I have the length, and so that's the overall length of the muscle. On the y-axis here, I have the amount of force that can be generated. Okay. It looks something like this. And so, you have a region where, when it's really, really short, the muscle can't really produce much force. But then as you kind of get longer and longer, the amount of force it can produce increases until you reach this area, which we call the plateau area. Okay. And so in the plateau region, in the plateau area, this is kind of the maximum amount of force that the muscle can produce. Okay. And so we call this region here, and that's not very good. Actually, a little bit too wide. And so this region here, under which the muscle can produce the maximum amount of force, we call this the optimal lengths. Okay. And that concept there is kind of really important to know. Okay. And so if you notice here, I didn't draw any specific units for this curve here. Okay. It's all just kind of generic. And so every muscle kind of has this kind of behavior. And so there's kind of an ascending region, a plateau, and a descending region. But where this plateau takes place and how wide it is depends on the muscle's geometry itself. Okay. Okay. And so there's kind of two, I mean, there's a whole range of these kind of geometries and how they behave, but there's kind of two extremes that I kind of want you guys to understand from this section. Okay. And so on the one hand, if you have very, very long muscles, okay, what a long muscle means that you have a lot of sarcomeres, or you have a lot of kind of individual muscle units that are connected kind of in series, kind of end to each other. Okay. And each of those sarcomeres can kind of compress and elongate by a fixed amount. Okay, and so what this means is that the more of these that you kind of have together, that means the overall, of course, the overall length of the muscle is going to improve. But this also means that the optimal length, or the region of the width of the plateau region, is also going to increase. Okay. Okay. So if you think about it, this makes a lot of sense because each sarcomere has a curve that's like this, right? And so the more sarcomeres you kind of add together, each one is kind of increasing the length of the plateau region by, a certain amount. And so the more sarcomeres that you have in series, kind of the more the length of this plateau region is going to increase. Okay. Okay. Number two. And so the opposite of a long muscle, of course, is a short muscle. Okay. And so a short muscle is kind of the opposite. And so instead of having lots of sarcomeres connected end to end, they have kind of a very few amount of sarcomeres that are connected end to end. And so, of course, you would expect the opposite to occur. And so instead of a very wide plateau region, this has a very narrow plateau region. Okay. Okay. And so that's kind of the two extremes. Okay. And that's kind of an important point to know, because depending on the geometry of the muscle, that tells you how many sarcomeres that there are in series, and so that's going to change the width of its optimal region. Okay. Okay. And so that's the force length relationship. Okay, so everything we talked about is kind of the relationship between force and length in a muscle. Okay. We also have kind of not exactly as formal as this, but an informal kind of relationship between the magnitude of the force that the muscle can produce and its cross-sectional area. Okay. And so in general, if you have a much wider muscle, or muscles that are wider than the other ones, have more sarcomeres that are packed together in parallel. Okay. And so the difference here is important, because when we talked about the length here, we talked about sarcomeres end to end, and so they're forming a chain. But when we talk about sarcomeres in parallel, they're kind of all kind of sitting next to each other, kind of like a parallel circuit. Okay. Okay. And generally speaking, the more sarcomeres that you have lined up in parallel, the more force the muscle can produce. Okay. And so what I mean by force magnitude is that when all the muscles are engaged at the same time, that would mean a higher kind of magnitude of force compared to the other ones. Okay. And so with this one, we also have kind of two extremes. And so we have kind of slender muscles versus wide muscles. Okay. Right. So slender muscles don't have as many sarcomeres that are in parallel to each other. Okay. Um, and so that means that the maximum amount of force that they can produce is limited. Okay. Okay. On the other hand, we have thick muscles. Okay. And so thick muscles are the opposite. And so because they have more sarcomeres kind of packed in parallel, the amount of force that they can generate is much higher. Okay. All right. And so that's the relationship between force and cross-sectional area. Okay. One thing that I want to say too, kind of before we move on to from this ideas of force and length, is that this curve right here doesn't account for the passive elastic properties of the muscle. Okay. Remember, one thing that we said before was that because muscles they behave like elastic solids. when you kind of stretch them beyond their certain length, then they will also exhibit force. Okay, and so right alongside this, there's another curve. We didn't really talk about all that much, but we call it the passive force length curve. Okay. Okay. And so with the passive force length curve, this the muscle could just naturally will produce force when it's kind of stretched beyond a certain length. Okay. And so the total amount of force that the muscle can exert is actually a sum of these two together. And so if you add up these two curves, okay, you're going to get a kind of a combined curve like that. And in purple, that combined curve is the combined amount of force that the muscle can generate from both its active and the passive components. Okay. So that's something that's kind of important to know. Okay. And so if I were to sum up these two, um, you know, generally speaking, when you have a muscle in the body, um, the longer muscles tend to be more slender, and the shorter muscles tend to be a lot thicker. And so long muscles will have kind of a wider plateau region, but the plateau won't reach very high. But for the short muscles, they are often a lot thicker. And so they may have a very thin plateau region, but it may reach very, very high. And so that's kind of the trade-off that you get between those two. Okay. Okay. All right. So that's kind of the most important points, I think, from this section. Okay. Let's go and move on. And so the next section that we went over was human motion kinematics. All right, and we spent quite a bit on this section because there's a lot of computations. And so I'm not going to, I'll go over kind of how to do the computations in general, but just know that we can apply, just know that the homework problems and the example problems that we did in class are a very good practice for these ones. Okay. Okay, and so in human motion kinematics, what we're interested in computing here is we want to be able to characterize the motion of the human body in terms of the joint angles and the joint angular velocities and angular accelerations. Okay, and so that's kind of our goal. Okay, and so those are the main things that we're hoping to compute here. Okay, and the way that we do this is we make use of some fairly modern technology, which was motion capture. Okay? Okay. And so remember, the idea with motion capture is that you put on a suit, and then at certain key locations on the body, you're going to put these reflective markers that's going to be picked up on a camera. Okay. Okay. All right. And so if you kind of look at it visually, it may look something like this. And so let's say that we have an arm here as the fist. Okay. And maybe you'll have kind of reflective markers kind of all throughout here. Okay. Okay. All right. Okay, and so that's kind of the idea with motion capture. Okay, and so we spend most of the time in this section talking about, if we do have this marker information, how do we actually use that to compute our joint angles? Okay, because it's not immediately clear, because the markers, I mean, you can track their XYZ locations in the you can track their XYZ locations in the using the cameras, but how to actually compute joint angles from these was kind of the subject of our discussion. Okay. And so in addition to like a lot of the, I would say, vector algebra, vector kind of calculus that you have to learn to do these, and you can look at the homework problems to do that, there's a lot of kind of important conceptual information that goes along with this as well. Okay. And so in every motion capture setup, um, the way that we kind of establish joint angles is by talking about coordinate systems. Okay. And so what this means is that for each body segment where we're going to place reflective markers, we're going to be establishing several different local coordinate systems. Okay. Okay. All right. And so there's mainly two that we're going to do, and we work with this quite a bit in our homework problem. Okay. And so the first is what we call, I'll start with the tracking system. And so we started with the tracking coordinate system. Okay. And so with the tracking coordinate system, this was a coordinate system that's established, and its main goal was that the tracking coordinate system was always going to be visible throughout the entire motion. Okay. I apologize. Let me pause one more. Right, sorry about that. Okay, so the tracking system, usually you establish this with markers that are placed in locations that are always going to be visible. So you should always see them in the motion. Okay. Okay, so often we call this the TCS for short. Okay. All right, next we have the anatomical coordinate system. Okay. And so the idea with the anatomical coordinate system is that this one is going to be, or the coordinate axes and the origin is going to be placed on the underlying bones within the body segment. Okay. Okay. And so the idea behind the anatomical coordinate system is that this is what's mainly used to establish joint angles in between the different adjacent body segments. Okay. And so we call this the ACS. Let me write that down. Okay. Okay. Because the joint angles, the way they're specifically defined in anatomical or biomedical literature is the angles between the bones inside your body. Okay. Those aren't always the easiest to observe. And so, that's why we established this anatomical reference frame to help us kind of track them. Okay. The problem with the anatomical coordinate system is that, oftentimes in order for them to match up with the bones underneath the body segment, the trackers have to be placed on kind of very specific locations on the body segment. And these may not be the most convenient in terms of tracking because as the person goes through the motions or as the person kind of, does their thing, he may block some of the markers such that they're not always going to be visible. Okay. And so that's why you need two. And so you need one coordinate system, the tracking coordinate system, so that you always kind of have a way to track the movement, no matter what the person seems to be doing. And the other coordinate system is actually used for the calculations. Okay. Okay. And so how these two are related is through transformation matrices. Okay. And so this is kind of what we spent the majority of our time doing. Okay. All right. So what a transformation matrix is that it's a matrix. It's a square matrix that defines, how two different coordinate systems are related to each other, both in terms of, the angles at which they're rotated by, as well as, the translation between their origins. Okay. All right. And so in 2D, I'm going to focus my analysis here on 2D. Um, for 2D, we actually mostly work with a three-dimensional transformation or 3 by 3 transformation matrix. Okay. Okay, and so it often looks something like this. And so we'll have cosine theta, sine theta, minus sine theta, cosine theta. Okay. Okay. So that's the transformation matrix we usually work with in 2D. Okay. And so we have sine and cosine terms, okay, where the angle in these sine and cosines, this angle is the angle of rotation, or kind of the relative orientation rotation angle between the two coordinate systems. Okay. Okay. And XO and YO, this is the location of the origin of one system relative to the other. Okay. Okay. All right, and so when we're building these transformation matrices, usually we kind of build them, or the kind of the easiest way to build these is to start with the transformation matrix between a reference system or a kind of a lab system, transformed into a one of the local systems, okay? Because that's usually easiest to do. Okay. And so this is what we did in the homework. And so this is usually whenever you have coordinate systems with lab as one of the systems. Okay. And so remember, usually when we denote these transformation matrices, we have to define the two systems within the symbol. Okay. Right. And so if we had a transformation matrix that's denoted like this tells us that this is a transformation between a local coordinate system, which is the TCS, and the lab frame, which is always the fixed reference frame. Okay. Okay. And so we usually build these systems like this. And so our bottom row is always 0, 0, 1. Okay. And we build this kind of column by column. And so this first column here, okay, this first column is the local x-axis. Right, so that's the x-axis of the local system, which is TCS, relative to the previous frames, which is the lab frame. Right, and so the reason we use the fixed frame for this is that when you're kind of defining local axes, it's a lot easier to use a fixed frame for this compared to kind of a local frame like another ACS. Okay, and so usually when we're computing is we first establish them relative to the lab. Okay. Okay. And so that first column there is the local x-axis. This column right here is the local y-axis. Okay. And we're going to define these local x-axis, local y-axis in terms of a vector. Okay, so that's why we have x1, x2, y1, y2. Okay, because remember, whenever you establish a vector, you need both components here. Okay, and in the third column, this third column is still the same as before, and so this third column here is the location of the local coordinate system origin relative to the fixed origin. Okay. And so this is like parts 1 and 2 of homework 5, problem 2. Okay. Okay. And so part 1 and part 2, that's how we did this, and that's an excellent reference for you to study for the exam. Okay. All right. And so once you establish the transformation matrices relative to the fixed coordinate system, then you can start to play with these. And so, another important property, a couple important properties for transformation matrices are the swap property, as well as the, I would say, the multiply property. Okay. Okay. And so, let's say that we have lab R TCS. Okay. If we take the inverse of this, okay, then the result would be another transformation matrix, but it would kind of swap the order of the two. Okay. So we have TCS up top or on the left and lab on the bottom. Okay. Okay. And so the other important property for transformation matrices is this multiply property. Okay. And so if you multiply two transformation matrices and their inner labels agree. Okay. And so in other words, let's say we have something like this. So we have R1, 2, and we have 2 R3. Okay. And we perform a matrix multiplication on this. Okay. What we see is that for the first matrix that we're multiplying, we have 2 on the right side. And for the second matrix, we have 2 on the left side. And so this is a case where the two inner dimensions agree. Okay. And so when you multiply these two matrices, that inner dimension is going to cancel out. And you end up with a transformation matrix solely of kind of the outer dimensions. Okay. And so using these two properties, using some inverses and using some multiplies, what you're able to do is you're able to form transformation matrices kind of between any two systems on a motion capture setup. Okay. And I'll kind of lump this kind of first thing as well. And so kind of starting with this, forming the initial transformation matrices, combining it with the inverse property and the multiply property, in theory, you should be able to form transformation matrices between any two coordinate systems on a person's body. Okay. Okay. So any two coordinate systems, you should be able to find their the transformation matrix between the two. Okay. In particular, remember the goal for this whole human motion kinematics is to find expressions for the joint angles. Okay. And so what we want is we basically want to relate the transformation matrix to this expression right here. Okay. Because if we can get the transformation matrix between two ACSs, and so the ACS of one body segment and the ACS of another body segment, we can then relate the entries of that matrix with the sine or cosine to compute the angles. Okay. And so kind of using all these techniques, and so part of it is a little bit of problem solving, is that you want to form the right transformation matrix. Okay. Okay. And so I think in the example we did in class, excuse me, the kind of the challenge problem that we did in the homework, what you're looking for is the transformation matrix R between the ACS of the upper arm and the ACS of the lower arm. Okay. Right. And so this is usually not going to be given to you right away. And so, you're going to have to perform, all three of these kinds of operations in order to form this kind of transformation matrix here. Okay. And then once you have that transformation matrix, you can then use the entries of that transformation matrix to compute the relevant angles. Okay. Okay. All right. So I'm just about out of time, but I did want to talk about inverse dynamics just very, very briefly. Okay. For inverse dynamics, there's not much theory to it. A lot of it is just kind of practice with the method. But it's just like before, it's always important to kind of understand what you're looking for in this technique. Okay. And so with inverse dynamics, what we're looking for is, conceptually, it's the next step right after kinematics. And so after you measure kinematics, you can use that information together with some measures of external forces. Remember, we talked about that in the gate biomechanics to compute, what are the internal forces in the body that are needed to produce this motion. Okay. Okay. All right. And so what we're looking for essentially is forces and moments. Okay. And the way that we do this, and so we do this, it's kind of a repeat of kind of the same thing kind of over and over again. What we do is we draw free body diagrams of each of the different body segments and use the equations of motion to compute the unknown forces and moments at the joints. Okay. Okay? And so that's all that really is to inverse dynamics. And so you're forming free body diagrams, you're including these internal forces, and you're using the equations of motion to find those forces. Okay. The only, I would say, nuance to this is that, when you're including the unknown forces and moments at the joints, they're going to be affecting two different body segments, right? Because that's the definition of the joint. It is the intersection between two adjacent body segments. Okay. And so when you're drawing the directions for these internal forces and moments, you want to make sure that the directions are opposite on the two different segments. Okay. And so, for example, for the knee, let's say that you're drawing the force in the x direction, force in the y direction, and the moment at the knee relative to the shank, okay, the lower leg. Then when you move on to the upper leg and you're drawing the same, reaction force at the knee, you want to choose the opposite direction for the forces and moments at the knee joint relative to the shank. Okay. And so if you look at the examples we did in class, I think this is very clear, but I think I definitely want to mention it so that you kind of are aware of it and Okay. All right, and so that went on a lot longer than I planned it to be. Maybe not that much longer, but a little bit longer. Okay, and so hopefully this video is useful for you as you study. But as always, you are definitely welcome to email me. You're definitely welcome to come to office hours if you have questions on the exam, and I'm more than happy to answer them to the best of my ability. Okay.